This is the exercise sheet on systems of linear equations, and I'll start with question 2, part A. So the first thing to do is to write out the augmented matrix for this system of equations. So the augmented matrix will look like this, and we just fill in on the right side. It's going to be -2, -1 and 8. And on the left side, we just fill in all the coefficients for x, y, and z. So the first column will be the x's, the second the y's, and the third the z's. So on the top, we have 2x minus y plus z. So that's 2, -1, and 1. Second row, we have x plus 2y plus 3z. That's 1, 2, and 3. The third row is 2x plus 2y minus z. So that's 2, 2, and -1. And that's the augmented matrix. We do our Gaussian elimination process on this matrix to solve the system of equations. So first off, I see a 1 over here on the left side. So I'm going to try and put that into the first row. So step 1 is going to be to swap row 1 with row 2, which gives me the following. So the first two rows are swapped. The next thing I want to do is get zeros down under that 1 on the top left in the first column. So I'll have to kill this 2, and I'll have to kill this 2. I'm going to make these next two moves in one go. So the first move is that I take away from the second row, I take away twice the first row. And that goes in there to where the second row is. And from the third row, I also take away twice the first row. And that goes in there to the third row. Now, technically, these moves should be done one at a time. But if I did that first move out, the red one, and wrote out the whole matrix, and then did the blue move and wrote out the whole matrix again, I'd get the same answer as I'm going to get by just doing them both here, writing it out once. So that's what I'm going to do. So my first row here is going to be the same as last time. My second row is going to be the old second row minus twice the first row. So 2 times 1 is 2, so I take that away from 2 and I get the 0 that I was looking for. 2 times 2 is 4, -1 minus 4 is -5. 3 times 2 is 6, 1 minus 6 is -5. -1 times 2 is -2, and then minus that would be +2. So I have -2 plus 2, which gives me 0. Then for the blue line, I get my 0 again, because I take away twice 1 from 2. Next, I have 2 minus 2 times 2, so that's 2 minus 4 is -2. 3 times 2 is 6, so we have -1 minus 6 is -7. And 2 times -1 is -2. So 8 minus -2 is 8 plus 2 is 10. Now the first column is 1, 0, 0, which is good. The goal of what I'm trying to do here with this Gaussian elimination is to get zeros everywhere under the diagonal. So this is the diagonal here, 1, 5, -4. That's the diagonal. So everything under that, I want 0. I have 0 here and 0 here. The last one I need is right here, this -2. Now I can see that I have a 2 on the first line here, and you might be tempted to use that 2 to get rid of that one. But if I did that, then that 1 would put another 1 down here and get rid of that 0. So I'm not going to use the first row anymore. I want to get a 0 here using this second row. Now using a 5 to get rid of a 2 looks awkward. But what I notice is that I have -5, and 0 here. So for the next step, I'm going to multiply that second row by 1 over 5, or divide by 5, whichever way you want to look at it. So 1/5 of row 2 goes into row 2 instead. So that's another valid move that I can make. After this step, I will have made all 3 kinds of valid moves. So the 3 valid moves that you can make in Gaussian elimination are to swap 2 rows, which if you think about it, changing the order of your 3 equations doesn't really change the solutions, so that's valid. I can add a row to another row, like this one, which also doesn't change the solution, so it's a valid move. Or I can multiply a row by a constant. In this case, multiplying it by 1 over 5. And that's the three things that I'm allowed to do, or the three kinds of valid moves. So let's make this move. My first row stays the same. So first and third rows haven't changed there. The second row is getting multiplied by 1 over 5. So minus 5 times 1 over 5 is minus 1. Same thing in this position. That's still a 0, because 0 times 1 over 5 is 0. And the same thing over here. 0 times 1 over 5 is 0. Now if I wanted to, I could go again and multiply that second row by minus 1 to get positive numbers there. But I don't have to do that. So I'll just go ahead for now and use that minus 1 to get rid of that minus 2 below. And the way I'll do that, I'll say row 3 minus twice row 2 goes in there to row 3. So I'm going to have my minus 2 below, and that's going to be minus 2 times minus 1. So minus 2 times minus 1 is plus 2. So I'll have minus 2 plus 2 is 0. So that'll work. So in my next line, my first two rows are not going to change. And in my last row, I have 0 minus 2 times 0 over here, still 0. I have minus 2 times minus 1, which is minus 2 plus 2 is 0, as I wanted. I have minus 7 minus 2 times minus 1. That's minus 7 plus 2 is minus 5. And finally, I have 10 minus 2 times 0, which is still just 10. Just in case there was confusion there, I'll look at this one again. So there I had minus 7 minus twice row 2. That's minus twice. What I have there in row 2 is minus 1. So that's minus 7 plus 2. Minus 2 times minus 1 is plus 2. Minus 7 plus 2 is minus 5. The process of Gaussian elimination is now done. We have zeros everywhere below the diagonal. Now what we want to do is solve the system of equations by using what's called back substitution. So that means we start at the bottom row and we actually put in our values for x and y, and we solve that bottom row for z actually, and then we substitute that value back into the second row and we solve that for y. Then we substitute z and y back into the first line and we solve that for x. So let's look at that third row there. That third row translated back into an equation just says that minus 5 times z is equal to 10. So that implies that z is equal to 10 divided by minus 5 is equal to minus 2. So z equals minus 2. I can now substitute that back into the second line. So the second line says that minus y minus z is equal to 0. So I can substitute that value in here for z, and I get minus y minus minus 2 is equal to 0. That implies that minus y plus 2 is equal to 0, which implies that y is equal to 2. Let's go back to the first line. We have y and z, so let's get x. That first line says that x plus 2y plus 3z is equal to minus 1. So I can take my values, z equal to minus 2, goes in there, and my value for y equals 2, goes in there. So I have x plus 2 times 2 plus 3 times minus 2 is equal to minus 1. Or x plus 4 minus 6 is equal to minus 1 implies that x minus 2 is equal to minus 1. X is equal to minus 1 plus 2, implies that x is equal to 1. So my final answer is x is equal to 1, y is equal to 2, z is equal to minus 2. And that's that system solved. Next we'll do question 3. So determine the values of k such that the following system has a unique solution and b more than one solution. So just to recap, if the system ends up having a unique solution, after Gaussian elimination, we will have an augmented matrix that looks like this. You see that we have our zeros below the diagonal, so we're done with Gaussian elimination. And in that last line, we have an equation that we can solve, where we have a33 equals b3, whatever those happen to be. And where, a33 is not 0. That system would have a unique solution. If there was more than one solution, then we would end up with a matrix that looks like this. You can see there that the last line, the last row, is all zeros. So there you'd have your free variable, and you'd solve then with a free variable where you get an infinite set of solutions. That's where you get the infinite set of solutions. The third option that we won't see in this question, but it can occur, is that you have no solution. And no solution looks like this. You see there on the last row, I have 0, 0, 0, and then on the right side I have something that's not 0. So if you translate that back as an equation, you get 0x plus 0y plus 0z is equal to b3, whatever that is, something that's not 0. So that's essentially b3 equals 0, where b3 is something that's not 0. So there is no solution there. You just have an equation that's obviously not true. That's what you call inconsistent or no solution. In this question we won't see that last one. So part A is unique solution up here. Part B is for more than one solution, which is going to look like this. So let's start off, do our Gaussian elimination and see where we end up. The augmented matrix for this system looks like this. The first row was x plus y plus kz is equal to 2. That's where I got 1, 1, k and 2, and so on. So we're going to do Gaussian elimination here. Now the nice thing I see first is that I have a 1 in the top left. So I'm going to use that to get rid of that 3 and that 2 underneath it. So first thing, I will say row 2 minus 3 times row 1 goes in here to row 2. And row 3 minus 2 times row 1 goes in there to row 3. So my first row here is the same as before, 1, 1, k, 2. My second row, that is going to be the old second row minus 3 times the first row. So 3 minus 3 is 0, as I wanted. 4 minus 3 is 1. 2 minus 3 times k is just that. Nothing more I can do. And I have k minus 3 times 2. That's k minus 6. For the third row, I'm taking away twice the first row. So I have 2 minus 2 times 1 gives me my 0. I have 3 minus 2 gives me 1. A lot of 1s here, it's working out very nicely. And I have minus 1 minus 2 times k. Minus 1 minus 2k. And I have 1 minus 2 times 2. So that's 1 minus 4 is minus 3. Well, this all looks good so far. Next, I want to get rid of this one, make that a 0. And I'll do that using the second row. Don't be tempted to use the first row or you'll get rid of your 0 on the left. So I will say that row 3 minus row 2 goes in there in row 3. So my first two rows are not changing. And my last row is the old row 3 minus row 2. So I had a 0 there, I still have a 0 here. 1 minus 1 is 0, as I wanted. And then I have minus 1 minus 2k minus 2 minus 3k. So I'll just work that out over here. Minus 1 minus 2k minus 2 minus 3k. That's minus 1 minus 2k minus 2 plus 3k. Minus minus is a plus. That's equal to minus 3 plus k. So that goes in. Minus 3 plus k. And then I have minus 3 minus k minus 6. So that's minus 3 minus k plus 6 overall. So that gives me eventually 3 minus k. Now we're done with Gaussian elimination. The next thing is to say for what values of k do we get a unique solution or more than one solution. So for a unique solution, I need this here to be not equal to 0. That's for part A. So if that's not equal to 0, then I get a unique solution. Remember that for there to be no solution or infinite solutions, I'd have to have all zeros on the left side there. If I had all zeros in the whole row, that would be an infinite set of solutions. If I had all zeros on the left and something non-zero on the right, then that would be no solution. But either way, to have a unique solution, that cannot be 0 there on the left. So let's write that down. Minus 3 plus k is not equal to 0. Well, let's find for what values is minus 3 plus k equal to 0. That implies that k is equal to 3. So for k is equal to 3, that's 0. You'll notice also that if k equals 3, that's 0 on the right there too. So we know that if k is not equal to 3, that implies that minus 3 plus k is not equal to 0. And it also implies, 3 minus k is also not equal to 0. So in that case, where k is not equal to 3, k is any number except 3, then I have a unique solution. That's a unique solution. So that's part A. The values of k for which that system has a unique solution is k is not equal to 3. That's the condition. Any other value of k is fine as long as it's not 3. For part B, when does k have more than one solution? Well, if k is equal to 3, then what I get on that last row is all zeros. So I'm just going to put this in a box here. K is equal to 3. That means that my matrix, I have a load of stuff there and I get 0, 0, 0, 0 there on my last row. So that's the infinite set. So part B is k is equal to 3. That's the condition to have more than one solution. So part A, k is not equal to 3 implies there's a unique solution. K is equal to 3 in this case implies that both of those terms are 0, 3 plus k and 3 minus k. And then we get the infinite set. So the last part then is to obtain those two solutions. So we'll start with the unique solution in the case where k is not equal to 3. So I've copied that over here. I'll start with that last line, go for a unique solution. So this is for the case where k is not equal to 3. So that equation then reads minus 3 plus k times z is equal to 3 minus k. That implies that z is equal to 3 minus k divided by minus 3 plus k. Well, that's just equal to minus minus 3 plus k divided by minus 3 plus k. If you look at the top there and multiply in that minus, let's say it's minus 1 times that. If you multiply that through on the top line, you get back that 3 minus k on the left. So I have a minus 3 plus k on the top and on the bottom. So I divide top and bottom by that minus 3 plus k, and I see that that is just equal to minus 1. Now I go back to my second row, and I can use that z equal to minus 1 here. So that second row as an equation reads y plus 2 minus 3k times z is equal to k minus 6. So I'm going to put in my value for z. I get y plus 2 minus 3k times minus 1 is equal to k minus 6. That implies that y minus 2 plus 3k is equal to k minus 6. Implies that y is equal to k minus 6 plus 2 minus 3k. That's just equal to minus 4 minus 2k. So that's y. And now we can use y and z to go back into the first line and get x. So that first line reads x plus y plus k times z is equal to 2. So I'll put in my values for y and z, and I will get x minus 4 minus 2k plus k times minus 1 is equal to 2. That implies that x minus 4 minus 2k minus k is equal to 2, which implies that x minus 4 minus 3k is equal to 2, which eventually implies that x is equal to 3k plus 6. So for part A, I have that if k is not equal to 0, then I have a solution, a unique solution of the form, where we don't know what k is, so our solution is going to be in terms of k. But if k is anything except 3, there's a unique solution, and it's of this form. X is equal to 3k plus 6, y is equal to minus 2k minus 4, and z is equal to minus 1. So next we look at the case of an infinite number of solutions. So that's when k is equal to 3. So now we look for the infinite set. Right, k is equal to 3 gives us the following matrix: 1, 1, 3, 2, 0, 1. Then we have 2 minus 3 times 3, that's 2 minus 9 is minus 7. And we have 3 minus 6 is minus 3. The last row then, we know is going to be 0, 0, 0, 0, because minus 3 plus 3 or 3 minus 3 both come out to 0. This line of zeros at the end is the reason that we have more than one solution. That's why we get the infinite set. So that equation just comes out to 0 equals 0. So no matter what x, y and z are, that's going to be true. So we really only have two equations for 3 variables. So one of them is going to be a free variable. So the new free variable that we're going to introduce, we'll call it t. And we're just going to say that it's some real number. So t can be any real number. And we'll say z is equal to t. So that's going to be our solution for z. Say that z equals t, where t is any real number. So now we can proceed as usual. Go back to that second line, which reads y minus 7 times z is equal to minus 3. So that means that y minus 7 times t is equal to minus 3, or that y is equal to minus 3 plus 7t. So I can take that now and go back to the first line. That first line says that x plus y plus 3 times z is equal to 2. So I can substitute in my values for y and z, and I get x plus minus 3 plus 7t plus 3 times t is equal to 2. So that implies that x minus 3 plus 7t plus 3t is equal to 2. So when I work that all out, I will end up with x is equal to 5 minus 10 times t. So at the end of all that, I have that if k is equal to 3, then I have the following solution set. X, so it's the set x, y, z, I'll write them here as a matrix, is equal to 5 minus 10 times t minus 3 plus 7 times t and t, where t is any real number. So that's my infinite set of solutions. So it's an infinite set of solutions, but not just any solution will do. It has to be three numbers x, y, z that satisfy this, where you pick any number for z and then that specifies what the y and x should be. So that's my final answer. If k was not equal to 3, I had a unique solution that depended on the precise value that k was. If k is equal to 3, then I get this infinite set of solutions with the free variable t.